Okay, hi, welcome to our second tutorial. Today we're going to talk about supervised learning. Just a few short notes. The first homework will be published today, first assignment. Okay, one short note. All right, so we'll cover in this tutorial the basics of supervised learning, which you should have seen the video lecture about this. So basically it's just a recap, and then we'll see two examples of supervised learning, of binary and multiclass logistic regression. We'll do it once from scratch with NumPy, and then using PyTorch, and just explain some things related to PyTorch that you will see later in the course many times. Okay, so let's go. All right, so let's remind ourselves a bit about the context that we're talking about, the framework of supervised learning. We have a labeled data set of n samples. So each sample is a feature vector x and a label y. Okay, so x is some d-dimensional vector coming from some sample space, while y is a label. In this case, for example, coming from the label space. For example, if we have C classes, then the label space is just integers from 0 to C minus 1. So we have a class label for each class. And usually our assumption is that these samples come from some distribution D over these pairs of feature vector and label. So it's a joint distribution. So for example, it's the label is not necessarily, it might be a stochastic label. Given the same features, you might get a different label in our assumption. So when we say model, what we're talking about is some parameterized set of functions. For example, or we call it a hypothesis class. So for example, this hypothesis class is known as the perceptron model. So we have some nonlinear function operating on an affine transform of the features. So you have the features, you take an affine transform using some weight vector W, add some bias, so this is a scalar here, and apply some nonlinear transform, and this is called the perceptron model. As you can see, it's basically just summing the inputs and applying the nonlinearity, weighted inputs, sorry. Okay. And our pointwise loss would be some function that maps the real label and the predicted label to some score, positive score. So for example, it could be a squared error, or for binary classification, this is the cross entropy error, which we'll see. We'll use it later. And now the task that we actually care about is that given this training set S, again, these samples come from some distribution D, we want to find a predictor, a hypothesis, or a function that minimizes this population loss. So we take the expectation over the entire population of labeled samples in D of this pointwise loss using our hypothesis. So this is what we actually care about, the out of sample loss. But the question is, can we actually solve this? Well, no, since I asked, it's probably no. We can't really solve this problem because we don't know D, and it's not feasible to actually compute this expectation, as you know. So what we actually do is we calculate an empirical loss using our data set. Okay, so we have our data set of n samples, as I said, and we calculate this empirical loss, which is, for example, here I'm just taking an average over my pointwise losses. And also, for example, usually there's a regularization term that does not depend on the data, only on the model. So all these things you should have probably seen in the lecture, just to recap. And a quick note about optimization, since I'm going to need it. You'll see much more about this in the next lecture, but this is just a quick reminder. So basically, when we say we're training our model, we mean we're updating the parameters. For example, in the perceptron model that I showed you before, our updating means changing the vector W. So we want to find a parameterization of our model such that we minimize our in-sample loss here under that parameterization. Okay, that's the goal of the optimization. So what you'll see again and again that we do in deep learning is use something called stochastic gradient descent. You'll cover it in the next lecture. I'm just showing this as a quick intro because we're going to need it in the examples. So basically the idea behind this is, given some kind of high dimensional function, that you want to minimize, you can use the gradient and move in the direction of the negative gradient, which will kind of tells you the direction of the decrease of the function. So, of course, if you have a like loss surface that looks like that, where you have some kind of non-convex function, then there may be multiple minima that you can find, and depending where you start, you might reach a different location. But the idea is that you update your parameters based on the negative direction of the gradient. So again, you'll see this in much more detail in the lectures. And the reason that we call it stochastic is that we actually don't compute this on the entire data, this loss and this gradient. We usually work with small batches, even of one sample. Usually when the definition of stochastic gradient set is when you do it on one sample, which means that you get a kind of a different loss surface each time that each subset of samples that you take. And this, for example, helps when you have non-convex functions, since when you have kind of these different loss surfaces each time, you might be able to get out of non-optimal local minima. But again, you'll see much more of this. So generally, like I said, we will work with functions where the loss is non-convex, and we can't really use gradient-based approaches to guarantee converging to any kind of global optimum. So usually we'll tackle this kind of optimization error. And two more key elements in this context of supervised learning are the concepts of generalization and expressiveness. So if you remember, what are the other sources of errors in this approach of supervised learning? So we have the error from optimization. That's one error, that we might not be able to find the global optimum. It's not guaranteed by anything. So other sources of errors, any ideas? Okay. Yes, exactly. So that's one thing, that we only work with the training set and we actually care about the whole population. So this is the generalization error. We train to minimize our empirical loss, but we actually care about the population loss. So we might fit our model very well on our data, but not well on the population. And the second thing is that we only consider a limited set of functions, our hypothesis class. For example, we said that in this example, we're using a perceptron model, but perceptron models are not necessarily very expressive. Maybe a much larger model would be able to approximate the function that we're trying to learn much better. So these are the other kinds of errors, and this is a nice visualization of kind of what's happening. Basically, in this hypothesis space, we're finding this function or this parametrization using our optimization, but the global optimum is somewhere else using the S data set. While if we were to actually optimize over the population, we might get to a completely different parameterization. So this is a generalization gap. And if we consider the space of all functions, then we also might have actually reached here. So this is the kind of the expressiveness of the model. Using maybe a stronger model with more parameters, we get more expressiveness. Okay, so now we're gonna see this example 2 times. So let's just remind us of what binary logistic regression is. So it's actually a classification model, even though it's called the logistic regression. We're trying to classify data into 2 classes because it's a binary logistic regression. Okay, and so again, we have these d-dimensional feature vectors x. We have targets. Our targets will be 0 or 1, just binary. Okay, and we'll use this perceptron model, but our nonlinearity will be the logistic function. So this is this sigma here. And the logistic function is just defined this way. It's 1 over 1 plus e to the minus z. So that's what we do. So the logistic function is a function in the range of 0 to 1. And what we're going to do, we're going to interpret it as a probability. So when we get this y hat, we're going to say that this y hat represents the probability of the class 1 given the features that we got. Okay, that's really one of the most simple and basic machine learning models. So let's just look at the logistic function for a second. I'm just plotting it here. It's kind of showing you. It's this sigmoid function. It maps the whole real number line into 0 and 1. Okay. So I think you saw this also in the lecture. To kind of solve this, we try to minimize the negative log likelihood, or actually maximize this likelihood. So we're going over our data set and calculating this likelihood. So again, it's a function of our parameters because of the way we defined the model. And what we actually do is minimize this negative log likelihood. Since it's equivalent, we can just take the log and can just open it and use the definition that we said, that y hat basically is just this probability, and you can get this term. So what you see here is this is a pointwise loss term between the ground truth y and the prediction y hat, and we're summing this pointwise loss over our data set. So we have n samples, so this is the full loss for w. Okay, that's it, really basic. And this pointwise loss is also known as the cross entropy error. Okay, notice that we got here from minimizing negative log likelihood. So sometimes it's called, sometimes that's a term that's used, and sometimes we just say we're using cross entropy as a loss, but in this case, same thing. Okay, so this is our optimization scheme. Now there's no closed form solution that we can find to actually get the best parameterization given this model, but if I show you how this cross entropy looks like, you can see it's a convex function. For example, here you can see the term. Since remember that y is binary, okay, so either y is 1 and this is active, or y is 0 and this is active. So you kind of get this function looks like that. So in the case that the ground truth is 0, the loss goes to 0 when the prediction is 0. In case that the ground truth is 1, the loss goes to 0 when the prediction is 1. Okay, simple. So everything here is convex. We can apply a gradient-based optimizer to actually find the best parameters, and we can converge into the best parameterization with arbitrary precision. Basically, you can find the optimum. Okay.
What was the y-axis?
Here, just the loss. Yeah, so goes to infinity basically. Oh, sorry. Not sure what happened. Yes. It's a probabilistic interpretation. It's the probability of the class 1. So one minus y hat is the probability of the class here. Okay. Okay, so the next step that we need to actually do some machine learning, we need to optimize, and like I said, since there's no closed form solution in this case, we will apply some gradient-based descent method. So we need to know the gradient. Okay. So I'm leaving this as an exercise for you. It's really simple. Actually, in the notebook you can see the solution, but you should try to do it because it will help you both in the homework and generally to understand what's going on. You can just compute the derivative of this y hat, of this pointwise loss basically, with respect to the weight vector. So y hat, remember, is the sigmoid of w transpose x plus b. So basically you just use the chain rule and get to the derivative of the pointwise loss with respect to w. So this is our gradient expression. Okay, it's dependent on y hat, y and x. Okay, makes sense. And you can see that, by the way, this is a scalar and x is a vector here with the same dimension as w. So you're taking the gradient of a scalar with respect to a vector, and you're getting a vector with the same dimensions. Okay, makes sense. Okay, so now let's look at some implementations, unless there's any questions. Okay, so the first example will be very quick. I just want to show you some kind of a basic way to implement everything from scratch using a NumPy, just classic Python-based machine learning. We're going to take a toy data set and apply this binary logistic regression on it. So this scikit-learn library is a kind of a very good general purpose library for many machine learning algorithms, and it also comes with nice toy data sets that we can quickly train. So we're going to just take one of them. I chose this data set called the Wisconsin Breast Cancer Database. It has 569 samples, and each sample has 30 features. This is kind of features that are extracted from cancer images, or tumor images actually. And we have two classes which are either the tumor is benign or it's malignant. Okay, so it's just the example itself doesn't matter. It's just needs some data to show the implementation. So nothing important is happening here. I'm just loading this this database from sklearn. What you should see after I process it a bit, I get this X matrix. This is our matrix of samples. So we have 569 samples of 30 features each, and each sample has a label 0 or 1. Okay, so this is our X and our Y. Okay, these are the feature names, by the way. We don't really care about them, and the target names are malignant, which is 0, and benign, which is 1. Good. Okay, just quick to show it quickly. So again, we have these samples, features. These are most of the features are just numbers, real numbers, and we have this class which we're trying to predict. Okay, usually in machine learning, one of the core steps is to split our database into a chain and test set. I'm sure everyone has seen this if you have any kind of experience at all with machine learning. So I'm just doing a basic split here to a 30% test set size, and I'm getting now these two pairs of X and Y. So I'm getting, this is my training set, and this is my testing set. Nothing too interesting going on. I just want to get to the actual model. So I'm also scaling the features here. I'm computing the mean of every column, since I want to scale the features to 0 mean and unit variance. Okay, so I'm just going over the columns, computing the mean of each column. So I'm getting this mu, which is the mean of each feature, and I'm just doing the simple transform to scale it. Okay, scale my data. So that's it. That's just setting up the data. Now let's look at the model. So we'll implement it based on all the equations that we saw, and using the gradient-based optimization that I explained. Okay, so this is the whole thing, just under 30 lines of code. Let's look at this fit function here, which basically this is what calculates our parameters. We're taking our data, our samples X and our labels Y. First thing, we initialize our weights to some random number. We're taking D here is the number of features, and N is the number of samples. So we're creating a weight vector with D plus 1 features or weights. And the reason is that I don't want to have a bias term. I don't want to have a bias because then I would have to calculate the gradient of the loss with respect to the bias. And I just showed you an expression of the gradient of the loss with respect to the weights W. I don't want to derive another one, so what I'm going to do, I'm going to add the bias to the data. So let's look at this. Let's look at this example. So I'm just doing it for a fixed number of iterations here. I'm taking my data. Okay. I'm adding a column of 1s to my data. This will be kind of like the bias because it will multiply with this extra dimension in the W. Okay, this is also known as the bias trick. After I have this X with bias, I predict the probabilities. Okay, so remember our model. What it's doing is predicting the probability of the class 1. So let's look at this implementation of the predict proba function. Can start looking for him. So all it's doing is basically exactly as the definition. We're taking the affine transform. We're doing a dot product between this matrix of N D, okay, our data samples and D features for each sample, and multiplying it with our weight vector. It's actually D plus 1 if it's with the bias, but it doesn't really matter here. Just so you understand the dimensions. Okay, and then we're getting our. This is kind of the raw score before we apply the logistic function. Remember that the logistic function maps the real number line to 0, 1, so we interpret it as a probability. So after we get this raw score Z, we can apply the logistic function that we implemented before and get the probability for each sample of being the class 1. Okay, so then that's our Y hat here. Okay, we got the Y hat. Now let's compute the loss. Loss is just by definition. This is the cross entropy, so it's Y time minus log Y hat, and 1 minus Y minus log 1 minus Y hat. Exactly as the as the formula that we showed, and we derived the gradient of this loss with respect to the W, okay? So now after I compute the loss and I derived manually the formula for the gradient, I can just apply this formula. So this is the formula. Remember it was y hat minus y times x, but here x is a matrix. Okay, so I'm applying it like this with transpose in the beginning. But if you look at every row here, it's exactly the same gradient calculation as we showed before. Okay, so again, I took my data, calculated the probability of each of the class 1. This is the y hat, using my current weights. Then I calculated the loss and its gradient. And using the gradient, I'm updating my weights. So this is the gradient step here. Okay, and we have some learning rate, which should be a small number, so we don't make large steps. Again, if the function is if it changes rapidly and you take a large step, then you might actually increase the value of the function, not decrease it. That's the idea. But again, you'll see a lot about optimization in the next lecture. So this is just the basic idea. So that's the whole model. Just fitting it like that. Let's run it. Okay, so I'm going to run for 500 iterations with a learning rate of 0.01. I'm fitting into my train data. So this is just running that loop that we saw and plotting the loss each time. I didn't actually use the loss for anything, just for plotting. What I used is the loss gradient. Okay, and we can see the loss is going down. Not surprising. It means we implemented the gradient descent correctly. If I just calculate now the accuracies on the train and test set, we can see that the model actually learned something. Yes. Yes. Here it's not SGD. It's not stochastic gradient descent. This is real gradient descent. You just take the whole data set and compute the gradient with respect to the whole data. And this is a toy data set. It's a really small and simple problem, so it's not really a problem. In real application that you will see, then you can't fit your whole data set in memory. So you'll need to work with batches anyway. As I explained before, when you work with batches, you also get the benefit of the fact that the loss function keeps changing, the loss surface kind of, and it helps with the optimization. But again, more on that in the lecture. Okay, so that was our first example. Now let's see a different kind of the same idea, but extended a bit and using different tools. Okay, unless there are any questions about the first part. Okay. So in the second part, we're gonna do the same thing, but for multiple classes. Now, let's say we have more than 2 classes. It's not a binary problem anymore. Okay, so can we still use logistic regression? What do you think? Yes. Why? Any ideas? Right. Okay. Well, you can do basically. I think the first easiest approach is to just use the binary classification that we had, and train a model for every class. For example, you train a model to say it's this class and not every other class. So this is a kind of one versus rest scheme. You can predict and use that, but the problem is that what you'll get is not you won't get a probability distribution over the classes. So if I have a sample, I won't get. I can use my multiple classifiers. Each will predict a different probability of that class, but I won't get a nice distribution that tells me what's the probability of it being each class. Okay, so that's kind of what I want. Yes.
So instead of one output, you might have
Sorry.
one of the three outputs instead of one. So you have one of the.
Exactly. Okay. Yes. So in the multiclass case, as we're gonna see, we're gonna use a different label. Just instead of a binary label, we'll use a vector label, which represents the probability of each class. Exactly. Okay. So that's the idea here behind the basic multiclass version. So first, let's define a function called Softmax, which is again it's a very important function that you will use not just for this simple multiclass logistic regression example. It's one of the common layers at the end of deep neural networks. So what Softmax does is given some vector z, it turns it into a probability vector. So you're taking the element-wise exponentiation of z divided by the sum of that element-wise exponentiation. So you get a, it's a vector valued function. It returns a vector, and it's a multivariate function, so it takes a vector. Okay, and it gives you, it kind of squashes your vector into a vector of 0. Of each element is between 0 and 1, and the sum is 1. Okay, and our multiclass model now will look like this. So we'll use Softmax here instead of the sigmoid function. Now, X is the same, it's still a D feature sample, but we have a weight matrix now. Now the matrix is a matrix that has it's like having C different weight vectors like before. So we have a weight vector for each class. Each weight vector is dimension D. And we have this bias term here, which is also now a vector of length C, because we need to add it to this vector that we get. Okay, so, and crucially, what we get out of this whole softmax, remember, it takes a vector and returns a vector. We get a vector of length C, which represents the probability of each class. So we input this sample X, feature vector, and we get the probability of each class as an output. Okay, simple. Okay, but what will our ground truth be? So we're trying to get probabilities as outputs from our model, so we need some kind of ground truth to match that. So one way is to encode our ground truth labels. So instead of having a label 5, we encode it as a vector with the fifth, or vector of zeros with the fifth component to be 1. So this represents the kind of a delta distribution that with all the probability mass on the class 5. So this will be our ground truth, and we'll train our prediction vector, the output of the softmax, to try to get to these delta distributions. That's the idea. Okay, and the cross entropy loss, very similar to before, kind of an extension, is that we take the negative log of this probability, but we take the element of the ground truth class. Remember, this is a one-hot vector. So this multiplication here selects, for example, the fifth element of this negative log probability. So we're taking the negative log probability of the correct class and using that as our pointwise loss. Okay, makes sense. It's just like before that we took the negative log and used it as a loss. Okay? So this is our cross entropy. Now, the data set that we'll use this time, just for an example, we'll use a data set called MNIST. This is a very famous data set, which was once used to benchmark actual algorithms. Today, it's really considered a toy problem, which is completely solved. It's a database of handwritten digits, where we need to predict what number it is. So I'm gonna skip this whole code that loads the data set. You'll see lots of it in the homework. So I'm just gonna show you. These are samples from MNIST. Okay, these are 28 by 28 images with one color channel. They're grayscale. Okay, and each image is of a number, and we have a label what the real number is. Okay. Now, something to note here that we're actually using SGD here. This is a case where the entire data set might not fit in memory. Maybe MNIST is not too large, but usually when you're training on images, then you do use SGD, which means you split your data into batches. So for example, what I'm showing you here, I'm taking the first batch of data from my data set. I have this thing called the data loader, which you'll see in the homework, and it will be explained much more. Yes?
What is SGD?
Stochastic gradient descent. Yeah, it's the version of gradient descent where you don't compute the loss and its gradient on the whole data set. You do it either on one or a batch of samples. Stochastic version. Okay, and what I'm showing you here is that I'm getting a batch of size 128. So this is a 4D tensor. Like I said, when working with images, usually we work with 4D tensors. So we have 128 samples. Each sample has one color channel, and 28 by 28 is the dimension of the image. Just an example here. Okay, so now that our data is in place and we understood the model, let's implement it. This time we're going to use PyTorch and its tensors, and we're going to skip the gradient calculation. We're going to use something called autograd, which is a functionality that basically calculates the derivative for you of anything. So you can have an arbitrary computation, get a number and then say I want the derivative of that number with respect to any of the input tensors that was a part of that calculation. So we're gonna go deeply into that, and in the homework too, you'll actually implement something like that yourself. But right now, I'm just gonna kind of explain it as a prequel to the next lecture. So the first thing that we need is implementing the softmax. Is to implement the softmax. Remember that it's e to the z divided by the sum of e to the z. There's a small trick here that that's important. So we take our softmax, we take our vector z. Actually, it's a batch now. Okay, so since we're working with batches, so it's not just one vector of c class probabilities. It's a matrix n by c. So we have n samples, and we need to calculate the softmax of each row. Okay, the small trick that's needed here is to actually subtract the max of each row from z. This is for numerical stability. So we're taking the highest score and subtracting it from all the scores. That's what's going on here, and you can kind of look at it later if you want to understand what's going on with dimensions. Simple broadcasting here, as I explained in the previous tutorial. So after we subtract the max, we do it by definition. We take the exponent, which is e to the z, and we divide e to the z by the sum of e to the z. Okay, and we get now these probabilities n by c, same dimensions as the input. We have the softmax of each row. Let's see an example. Sorry, skipped it. Let's see an example. I'm taking the softmax of this tensor. So the dimension here is 1, 3. Okay, it's a 2D tensor, dimension 1, 3. Applying softmax, I get something that sums to 1, and each number is between 0 and 1. Probability. Okay, so let's implement our cross-entropy loss for this version with 1 hot vectors as ground truth. So now we have this 1 hot y, and y hat is the probability of the classes that we will get from our softmax. And again, these are batches, so we're working with n by c matrices. Okay, and we just compute it by definition like that. Since the y's are 1 hat, we can 1 hot, mostly 0. We can just use the element-wise multiplication here between the matrices, and we sum over the whole thing. So we get the sum of the losses, sum of the pointwise losses. Okay, so this is a function that I will need later to create these 1 hot vectors. It's not important. You can look at it afterwards. Now let's look at the model itself. So this is the whole model. All I'm doing here is creating 2 tensors. One tensor for my weight. Remember, the weight is now a matrix. Okay, it's a matrix with dimensions n features and n classes. I have kind of a weight vector for each class now. Okay, and I have this requires grad equals true thing. This is where the magic happens. When I specify that, it will mean that I can do any calculation I want with these 2 tensors. And afterwards, when I get some kind of final number like a loss, I can compute the gradient of that number with respect to this tensor. Okay, I'll show kind of an introduction to that. And this is what you'll see in the lecture is the way to calculate it is called a backpropagation algorithm. You'll see it in the next lecture.
So what would be the difference if you do it for false?
Require grad equals false. It means that when you do some mathematical operation, let's say I take this w and multiply it by 2, that multiplication, if I say requires grad equals 2, is tracked. Some object is saved with the kind of what was performed, the multiplication by 2 and the data required to calculate the gradient afterwards using the backpropagation algorithm. You'll see the backpropagation algorithm in the next lecture. I'm just showing you this so you can kind of understand when you see it in the lecture how it's implemented. And like I said, you'll go much deeper into that when you do the homeworks. Wait, so I didn't actually finish explaining. So we have these 2 tensors. So this is just the dimensions as you saw previously in the model definition. We have this bias, so it's just a vector of the number of classes C. Okay, so now my model, my actual implementation here is in this forward function. Usually in deep models we divide our training into a forward pass where we compute the prediction, and a backward pass where we update the actual parameters using the gradient. So that's why it's called forward. Again, pattern that you'll see and you'll understand it more in the sequel. So basically, the whole model is, again, just doing an affine transform and then applying a nonlinearity. So I'm taking a matrix multiplication here of my data, n samples d features, by this W, which is the weights matrix. Okay, so again, I have a weight vector for each class, and adding the bias vector. This gives me my raw scores. Okay, and after that, I take the raw scores and compute probabilities. That's my y hat. So I get a probability distribution now. So now y hat will be n samples by c classes. Each row is a distribution of the class probability. Okay? Good. Okay, so now just let's try it without training. Let's create a model and take the first batch of samples. And I'm just gonna flatten it. I'm just gonna ignore the 1 by 28 by 28. I'm gonna flatten it into a vector. That's what this shape is doing. And I'm gonna take my ground truth labels. So this is a vector of the ground truth labels of the batch, and create one hot vectors from that. And then I'm gonna pass it through my model and compute the loss, just to see that everything works. So let's see. We took our batch of images, flattened it, so now we have 128 images that are flattened. So we have 784 features. Again, this is not a really good idea to process images this way, but it's just as an example. I just need kind of data. And so now we're just treating every pixel in the image as a feature. That's what this model is going to do. And as you can see, the one hot version of the y's is a batch of 128 one hot vectors. Okay, now the loss, I just used our cross entropy loss as we defined before. And notice that I get this tensor here, but I have this grad function added to it. So this is what I said about tracking. The fact that since I said required grad equals true for the parameters, all the operations on those tensors that happened when I said forward here, when I applied the model to the data. By the way, I'm not calling forward here explicitly because, I don't know if you noticed, there's this call method that calls forward. So if you use the model as a function, like I did here, it just calls the forward through the call. Okay, so basically what happened here, we have this some kind of pointer to some kind of extra data. So I'm just going to show it briefly. This is what actually allows the backward pass using the backpropagation algorithm. Since we said required true, then all these operations were recorded, and a computation graph can be built using these operations. So let me show you what I mean. I can visualize this graph. So I'm taking this loss, the number. This is a tensor containing a scalar, and what I'm seeing here is kind of the graph that produced it. We started with this weight matrix, and we used the matrix multiplying it by the x. Remember, and then we added the b, and we got the z, right? And then we applied the softmax. So softmax had a max component, and an exponentiation component, and a division. So you have the x division divided by the sum. So you have the sum here. So basically, you see the flow of all the operations that happen to compute this loss. And after the softmax, then a log was applied, and we summed over all the pointwise losses. So you see this kind of graph. So this is what, basically, keep this in mind when you see the kind of backpropagation algorithm. This computation graph is what's actually being traversed backwards. Okay, questions about that? Okay, so this is kind of an intro. It's not really the full picture, but you need to kind of understand it to understand the technical stuff in the implementation. So let's go to the last part, which is the training of this model. Now we'll again use SGD, just like before, taking the negative direction of the gradient to update the weights. But now we're not computing the gradient of the softmax manually. If you want, you can do that. It's a nice derivation, but we're not going to do it manually for the W and the B. We're just using what I showed you, this computation graph, and the fact that the PyTorch's autograd can actually compute the gradient of the loss with respect to both these tensors automatically. So what I'm showing you here is just a function that's doing the optimization here, which is going over the params, which is just a list of tensors, which will W and B. And since I said required grad equals true, I can compute their gradients using the backward function that I'll show you. And then I have this grad property on these tensors. Okay, so instead of manually hard coding here the gradient calculation that I computed by hand and then implemented, I can just say, take my W, for example, and take its gradient with respect to the loss, times the learning rate, and subtract it from the parameter value. This is our gradient step.
This is a single step?
Yes. Yes, this is just a single step. I'll call this function here during the training loop, which I'll show you. So this is a,
So,
yeah.
question about this function.
Yeah.
So does it refer to the size of the gradient, so it can make a bigger step for bigger gradient or smaller step for smaller gradient?
You can, well, you can implement any logic that you want here. You can take this grad, compute its norm, for example, and then choose the learning rate with respect to that. We'll see later in the course there are various more advanced optimizers. This is called vanilla SGD. So there are more types of SGD that do kind of these fancy tricks that the learning rate is not fixed but kind of adaptive to the magnitude of the gradient of each parameter. So this is a function that just evaluates the accuracy on a data set. I'm going to skip it because I want to show you. Yeah. Yes. Tensor, it's n-dimensional array. For example, here. Sorry?
Why do we need a few of them? Why do we need a list of them?
Because this is just a convenience. I want to apply the same logic to all of them. I have for example, in this example, I have W and B. These are my parameter tensors. In this case, W is a 2D matrix and B is a 1D vector. I want to take the W and update its value using a stochastic gradient descent step. So I have this gradient of the loss with respect to W, and I'm using that to update W. And you'll see where this comes from in a second when I show you the training loop. You'll see the source of the params. It's just a list of both of them. So now I'll show you the training loop. So this is a kind of the PyTorch recipe for training loops. You're going to see this pattern again and again. It's usually always the same or very, very similar, unless you're doing some kind of more advanced, like, for example, not supervised learning or things like that. So the idea is we go over the data set in batches. Again, the data can't fit in memory. In the forward pass, we take the batch and compute predictions, and we build this computation graph since we say we require grad equals true for all our parameters. So a computation graph is built. Then we calculate the loss, and we set okay, this is a technical detail that you need to remember. You'll see why, but basically you need to set the gradients, the existing ones, to 0 so they don't accumulate. Because in the backward pass, the backpropagation algorithm will calculate these gradients. It will populate what you saw, the param.grad, it will populate that field using the backward pass. So again, the backpropagation algorithm, very important piece of knowledge. It will be in the next lecture. And then the optimization step, you take the gradient and update the parameters like I showed. Okay, so let's look at what it looks like. I'm going to run for 10 epochs. Epoch is one run over the whole data set. And I'm just going to limit the number of batches because I want the training to go fast. This is a large data set, and I just want to show you that it works. Okay, so this is our model, creating a model instance, and let's see the code. Okay, so we're looping for just fixed number of epochs. We're taking our data loader and enumerating it. So this is what basically returns our batches of data. We have this. We're just adding an index here to plot it, to print it. But we're getting these pairs. So this is a batch of images, and this is a batch of labels, like I showed before. So this is, for example, the 4D tensor that I explained before. Then I'm taking this 4D tensor and just flattening it out. Again, this is not what usually happens in deep learning, but here I'm just going to treat each pixel as a feature, so I'm flattening every image and computing the one hot of the labels. Then forward pass, apply the model to my data, get y hat, which is the prediction of the class probability of each class for each sample, n by c. Okay. Then do the cross entropy loss between one hot and ground truth and prediction, get the loss. Now the magic, this is the backpropagation algorithm. You say loss backward. This goes over the computation graph that I showed you and basically calculates the gradient of the loss with respect to all the intermediate steps. And finally you get the loss, the gradient of the loss with respect to the input tensors that you care about, W and B. So this is the implementation of the backprop algorithm. Okay, you'll see it again, like I said in the lecture and the homework. And after I have this backward performed, then my dot grad field in each of these tensors is populated. Now the real grad is actually there. So now that it's there, I can pass this list of parameters. This is just a list of W and B. Pass it to my optimizer function. And it will go over W and B, take the W, take its grad and update W, take the B, take its grad and update B. This is the step that I use to update my parameters. Now I have new parameters. Okay, and then just keep going over these batches. When the batches are done, I'm finished with my epoch, and then I go to the next epoch, and I keep updating my weights parameters all the time. Any questions about this?
So the reason you do this computational block is like to separate the calculation to little pieces. So you can use the chain rules to do like the 10.
Yeah. Yeah. Since the autograd thing, the autograd functionality, it allows you to compute the gradient of the loss with respect to the input, and it doesn't matter what calculations you did in the middle. You can do arbitrary calculations with these tensors, well, almost arbitrary. As long as it's differentiable, it will save a step in this graph. This graph will be built, and the backward will traverse it and calculate your gradients that you need.
But there isn't an issue for like memory things.
Yes, there is. If your model is really large, then this graph can be really large, and yes, and there's lots of data that's saved in this graph. So yes, it is a factor. Yeah.
In the former example, you used one perceptron in the breast cancer. Here, how many perceptrons do you use? 10 or
10. It's like you have a perceptron for each class. That's why the W matrix is the dimensions are C by D or D by C. It's like you have a weight vector for each C, each class. Okay, so let's run this actually. Actually run, yeah. Yeah, I did it. I just didn't show it. I did it in this function. If I go back, you can see it. The reason is if you don't do that, then the backward will it won't just calculate the gradient, it will accumulate the gradient. It will take the current gradient and add it to the previous gradient. And that's actually a feature, not a bug. Again, more on that in the homework. And if you don't believe me that I zeroed it, then here. Okay, I did zero it. It's not exactly how you would do it in practice. This is just for an example. But okay, so now I ran this. Yeah.
Why did this example use in the regular
No, I generally need to zero it. There are some cases where you do want to accumulate gradients. We'll see that, for example, in the recurrent neural network tutorial. Some cases you do want to accumulate, so it's not a bug that they forgot to zero it for you. It's actually necessary to know when you need to zero or not. All right. So what we did now, we ran for a few epochs. You can see the losses going down, the training accuracy is going up, the testing accuracy is going up. I just trained it for 20 batches and 10 epochs here. So you can see the model is learning. The parameters are being updated each batch. Every time we're getting a better parameterization because we're going down this loss surface using gradient descent, getting better and better and better parameters. That's why the loss is going down, and that's why the accuracy is going up. Again, I didn't show the evaluate accuracy function. You can look at it later. Now you will be able to easily understand it since it's similar to this training loop, so you can look at it afterward. All right, so just a few notes to close. So this is a very basic implementation just to show some concepts, mainly with PyTorch, and kind of show you a preview of the autograd functionality so you can better explain the backpropagation algorithm. So this is not really a good way to work with images or anything like that. And the second point is that many of the things that I showed you are actually built into PyTorch. You don't need to implement a perceptron layer yourself. You have it built in. You don't need to implement Softmax. You don't need to implement SGD or any of the other fancy SGD-based optimizers that there are, or the losses. So but you have a lot of things built in, but it's really important to show it from scratch and understand what's going on under the hood and be able to implement it yourself. And I think you'll see that in the homework you actually get to do that. All right, so thanks. We're done.